Hello friends, I welcome you all to this class. This is linear algebra class, and today we'll be considering this topic, diagonalization of matrices. We want to know when a particular n by n matrix, that's a square matrix, is said to be diagonalizable. Now, an n by n matrix, let's just call the matrix A, is said to be diagonalizable if there exists an invertible n by n matrix P, let's just call it P, and a diagonal matrix, let's just call it D, such that this diagonal matrix is equal to P inverse of AP. That's P inverse multiplied by A multiplied by P. So this thing is just telling you that a particular n by n matrix, a particular square matrix, is said to be diagonalizable if you can find an invertible n by n matrix P such that this relation holds. So you can find an invertible n by n matrix P and a diagonal matrix D. So if you can find a particular n by n matrix P and a diagonal matrix D such that this diagonal matrix D is equal to P inverse AP, then that matrix A is said to be what? Diagonalizable. This simply means that the matrix A is similar to the diagonal matrix D. So a particular n by n matrix, a square matrix, let's just call it A, is said to be diagonalizable if it is similar to a diagonal matrix D. This is the simplest definition you can give. If it is similar to a diagonal matrix D, when we study the similarity of matrices, if you have two matrices A and let me say matrix A and matrix B, right? Then matrix A is similar to matrix B if you can find what? An invertible n by n matrix, that's a square matrix, you can call it P, such that this matrix B is equal to P inverse AP. So this is just similar to what we have said here. So the matrix A must be similar to a diagonal matrix D before we say that it is what? Diagonalizable. Then we have some theorems that can help us to verify whether a given matrix is diagonalizable. The first theorem is saying that matrix must have what? N distinct eigen vectors. So if the matrix has n distinct eigenvectors, so this means what this thing is telling you is that for you to use this theorem to verify that a particular square matrix is diagonalizable, you must find the eigenvectors corresponding to each of the eigenvalues of the particular n by n matrix. So you first of all compute the eigenvalues and get the corresponding eigenvectors. If the eigenvectors are linearly independent, then that particular n by n matrix must be what? Diagonalizable. Then we have a corollary. This corollary, I can say, is a neighbor or a close neighbor to the first theorem, right? Because this corollary is telling you that an n by n matrix, that is a square matrix A, is said to be diagonalizable if it has what? Distinct eigenvalues. Distinct eigenvalues. This is because if it has distinct eigenvalues, then if you compute the corresponding eigenvectors of each of the eigenvalues, those eigenvectors must be linearly what? Independent. So with that, we can go straight to this example and see what this corollary and the theorem is telling us. This particular matrix A is given to us, and we want to know whether this particular matrix A is what? Diagonalizable. So let's proceed. Solution. The first step is to what? Compute the what? The eigenvalues of this particular matrix. So let's just consider this for the eigenvalues of A, we need to solve. So for us to get the eigenvalues of A, we need to solve this simple equation. Determinant of A minus lambda I, where this I is the let me denote it as I sub n, because it is an n by n identity matrix equal to 0. So we need to solve this simple equation. So let's just clean here and create space. So this simply implies determinant of what is A? The matrix A is 0, 0, minus 1, 1, minus lambda multiplied by, what is this matrix A has what? What is the n there? That is the dimension. This is 2 by 2 matrix, right? This is 2 by 2 matrix. So our identity matrix must be what? 2 by 2. So we are going to have 1, 0, 0, 1. That's what we are going to have. Determinant equal to 0. So this is equation we have to solve. This implies determinant of, let's multiply this lambda and this matrix. So we are going to have, let's write first the first matrix A. Let's write matrix A first. Let's multiply this lambda and the identity matrix. This will give us lambda times 1 is lambda. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 1 is lambda. Determinant equal to 0. So let's subtract. This implies let's subtract 0 minus lambda. We are going to have what? Minus lambda, right? 0 minus 0, 0. Negative 1 minus 0, negative 1. Negative 1 minus lambda, 1 minus lambda. Determinant equal to 0. So this simply implies, so you know how to find the determinant of 2 by 2 matrices, right? You have 2 by 3 matrices A, B, C, D. The determinant will be A times D, that's AD, minus C times B. Or you can say B times C. Let's just say BC. So this will be the result. So let's follow the same thing. So this will be this times this. So minus lambda multiplied by 1 minus lambda minus 0 times 0 multiplied by 1 will be what? 0. So if you subtract 0 from any quantity, then you will get the same quantity you have before. So we have negative lambda multiplied by 1 minus lambda. So at the right we have 0 equal to 0. So this simply implies that what? your lambda, if you solve this, you'll be having what? Negative lambda equal to what? 0, which implies that what? Your lambda will be what? 0. If you solve the second one, you will now have 1 minus lambda equal to what? 0, which implies that lambda is what? 1. So this implies that lambda 1 is what? 0, and lambda 2 is what? 1. So the eigenvalues we got is 0 and what? 1. So are the eigenvalues distinct? Of course, the eigenvalues are distinct. 0 is different from 1, right? So from the corollary, it implies that what? A is diagonalizable, right? Since the eigenvalues are distinct, it implies that what? It implies that A is diagonalizable. So in this, we have come to the end of this class. Subscribe to this channel so that you will be part of our next subsequent classes. So we are going to solve more examples under this topic. Thank you. Have a nice day.